For the surface area, application of the differential surface area that we discussed before, let's take this example. The flux density coming from a charge Q is given by D equals 1 over 4 pi r squared AR. Determine the flux which crosses the portion of a spherical shell described by from theta less than greater than or equal to 0 and less than or equal to 90 degrees. So this is a spherical coordinate system because it's a spherical shell. And also, if you take note, the given vector d is also in spherical coordinates. So you can solve this by the flux, total flux. I will discuss more about this later on, but I will just give you the formula now, and we just evaluate them using the surface area, differential surface area. So the flux is just equal to the dot product of the flux density with the surface area, the vector surface area. And this is a surface area integral. And so this is a vector. dA is a vector and also D is a vector. If you take the dot product, so the result here, the flux is a scalar quantity. So in this case, our problem is in spherical coordinates. So what will be our dA? The dA that we will be using should be also in spherical coordinate system. So if you go back to our previous discussion, we already derive the area, differential area of a spherical coordinates, and this is that formula. This is equal to this one. We choose this one because it's in the ER direction. Why do we want that ER direction? Because the problem says, just copy this. The problem says we want to determine the flux that crosses to the spherical shell. So if you have a shell, a sphere, then there's a charge inside that. So this is a positive charge. And then there will be the result of this will be a flux density. And the direction of the flux density is going outward in that direction because it's just AR. The vector field that represent that is just equal to AR. So that's the direction of D. So that is our D. That vector D, vector field. Now, what we want is to determine the area that crosses a certain area, certain part of the sphere. So not the whole sphere, but a certain part of the sphere. And the sphere from that is being described where theta is greater than 0 and less than 90. So if we plot this into the spherical coordinates system, so this is our spherical coordinate system here. So this is the z-axis, this is the y, and this is the x-axis. And if you plot that 0 to 90 degrees is start our remember our phi or theta starts from the z-axis. So you start at 0 up to the 90 degrees. The 90 degrees is up to this one. So what we are just solving is actually the half of the sphere. The area of the half of the sphere, not the whole sphere, because it's just from 0 to 90 degrees. So if it's not 90 degrees, if it's 0 to pi, then, or 180 degrees, then that is the whole sphere we're talking about. But the surface area that is being described here is just from 0 to 90. So that's just the half of the sphere. So this half here will be the area. We want to determine the flux that crosses this area. So to do that, we use this formula here, the dot product. It's just a dot product of D and that surface area. Then we will be using the surface area here that we derived before in our previous discussions. This will be our dA, and our D is 1 over 4 pi r squared. So if we substitute this now, we have our flux will be equal to the integral of that surface area of d, which is 1 over 4 pi r squared in the r direction. And this is our d. We take the dot product with dA, which is r squared sine theta d theta d phi in also in the r direction. So if you take the dot product of AR dot AR, that's just equal to 1. And we can cancel out r squared and r squared. So it doesn't matter what is the radius of the sphere, because in this equation, the radius will disappear in the final equation for that flux. So it doesn't matter how much is the radius of that sphere. And we will discuss that actually later on in the previous chapter, next chapters that we will be taking. There's a reason why that's true. Then, but for now, we need to solve for this flux here. So this will be equal to, so because we have two differential, d theta and d phi, so we will be using two integrals. Then we have 1/4 pi, r squared is now cancelled. Then we have sine theta, d theta, and d phi. And AR dot AR is 1. So now what are our limits? For d theta, we know the limits for d theta. It should be from 0 to 90 degrees, or 0 to pi over 2 if you want. 0 to 90 degrees. But how about phi? Our phi, because this is the half part of the sphere, our phi actually is 1 revolution. We rotate it in that direction. That's 1 revolution. So this should be from 0 to 2 pi. That's phi, because that's our, here is phi. If you remember our phi, this angle is phi. So we rotate this in from 0 to 2 pi, because this is 1 revolution of the sphere, half of the sphere. So it should be 0 to 2 pi. Then we can now integrate this. This is again a multiple integration. So this will be, we can remove that 1 over 4 pi, the constant. Then we can start with the theta. So we can first remove the integral for phi. Our phi is from 0 to 2 pi. So let's start with the theta. And we have the integral from 0 to 90 degrees of sine theta d theta. Then I'll put d phi at this part. Then we need to integrate first this before we can integrate the final value. So what's the integral of sine theta? The integral of sine theta is this negative sine of, or cosine of theta. This is negative cosine of theta. But we need to take the limit from 0 to the 90 degrees. So upper limit minus lower limit, this will be negative cosine of 90 degrees minus negative cosine of 0. Negative cosine, or cosine of 90 is 0. Cosine of 1 is 1. Negative, negative, so it will become positive. So this whole thing is just equal to positive 1. So therefore, our integral now will be just equal to 1 over 4 pi times the integral of d phi from 0 to 2 pi. And what's the integral of d phi? That's just phi. So this will be 1 over 4 pi, the integral of phi from 2 pi, or 0 to 2 pi, upper limit again, minus lower limit. So 1/4 pi, upper limit 2 pi, minus lower limit 0. So you multiply it with 1/4 pi, then cancel pi, 2 over 4. So the answer now is our flux will be equal to, it's just equal to 1/2. The unit of this is in coulomb. So this is how we used differential surface area. And what are we actually doing here is we're just solving for the total area. You can do this one because it's just half of the surface area of the whole sphere. You can just compute without using the integral. You can just compute for that area because you know how or what is the formula for the surface area of a sphere. If you divide it by 2, then you multiply it with our d, the magnitude of d, then that will be the total flux. So you can also do that, but because the limit is from 0 to 90, so if I change that limit, instead of 0 to 90, from 0 to somewhere between 45 or 30 degrees, then it will not be possible using that method because you don't know it's one fourth, one third of the whole sphere. So you need to follow again this method of evaluating a differential area. For the differential volume, so the next one, for the differential volume, see the only difference between a differential volume and a differential surface area, this one is just a double integration. For a differential volume, we do triple integration. So for example, if we are given a volume, or let's just take this example, determine or find the charge. Let's see, we have the charge in a volume defined by, in a volume that is described by these surface areas, described by the inequalities 0 for the x is less than or greater than or equal to 0 but less than or equal to 1. So if this is in meters, and we also have for the y-axis from 0 to, let's just make it simple, 1. And for the z, let's just make it also 1. From 0 to 1. Find the volume, find the charge in a volume that is described by this volume that is in the region covered by these three surface areas. If the charge density is given, let's call it rho v. So this is charge density, which is equal to, or which is being also described by the scalar field 30x squared times y. So this is in, let's say, microcoulomb per cubic meter. The unit for this, meter. So we want to find the charge. The unit for charge is microcoulomb. So how do we do that? So by using differential volume. So the solution, the total charge, which is denoted by Q, is this equal to the integral of that density, volume density multiplied by a differential volume, and this is a volume integral. And dv here and rho v, these are all scalar quantities, so we don't need to take the dot product. But we know that this is in x, y, and z coordinate, so the dv that we'll be using should also be in the rectangular coordinate system. So our dv in the rectangular coordinate system is just dx dy times dz. So given the limit now, our q, or the charge, now will be equal to the integral, because this is three differentials, so this should be triple integration. Rho b is 30x squared times y. Then dv is dx dy times dz. And what are our limits for the x? It should be from 0 to 1. They are all from 0 to 1. 0 to 1. Because they are being described by the planes from 0 to 1 in the x, also in y, 0 to 1, and also in z. So it's just a cube volume. And if you want to determine the total charge in that volume now, if this is our charge density, so we need to distribute this charge density into that volume. So how do we do that? We just multiply that density to that volume to solve for the total charge. So this will be equal to now for, let's take first dx. So we can integrate dx with respect to dx. So what will be the integral of this with respect to dx? It will be equal to, so 30y, this is just a constant. Integral of x squared is just x raised to 3 over 3. And we apply the limit from 0 to 1. So this will be equal to 30y times, or we can remove the 3 here. So this will be 30 over 3. We can just put it here times 10. 30 divided by 3. Then we have x cubed, upper limit minus lower limit. So 1 cube minus 0 cube. So this will be 10y. So this part will be equal to 10y. So we have, so this will be, we have still double integral left here. So 0 times 10y. The dx will now disappear in the equation, and this will be dy, and I just put dz at this part. So the next thing, the next that we want to integrate now will be this one with respect to y. So what's the integral of 10y with respect to y? That's just 10y squared all over 2. So that is 5y squared. And upper limit minus lower limit again from 0 to 1. So this will be equal to 5 times 1 minus 0. All that is just equal to 5. So we have now the integral of 5 dz from 0 to 1. And this one now, dz, integral of dz is just z. So this will be just equal to 5 times z. Then apply the limit from 0 to 1. Upper limit minus lower limit, 1 minus 0. See, the answer now is the total charge now into that volume being distributed through the charge density, not non-uniform charge density, will be equal to 5. And this unit is microcoulomb. So this will be microcoulomb. So the answer is 5 microcoulomb. So this is how we evaluate a volume using triple integral.